Space is vast and full of wonders. One of the most spectacular events is a supernova. Imagine a star much bigger than our sun exploding with unimaginable power. That's a supernova. It's like a cosmic fireworks show but on a much grander scale. For a short time, a supernova can outshine an entire galaxy. Then it slowly fades away, leaving behind a beautiful remnant of gas and dust. Supernovae are not just beautiful, they are crucial to our understanding of the universe. They are the cosmic furnaces where heavy elements are forged. These elements, like the calcium in our bones and the iron in our blood, are scattered throughout space. Without supernovae, life as we know it would not exist. Stars may seem eternal, but they have a lifespan just like us. They are born, they live, and they die. A supernova is one way a star can die, a spectacular and violent end. So what happens inside a star to trigger such an event? Stars are like giant pressure cookers. They have immense gravity pulling everything inwards. This inward pull is balanced by the outward pressure from nuclear fusion in the core. Fusion is like a giant, continuous explosion where lighter elements combine to form heavier ones, releasing energy. This energy is what makes the star shine. However, this balancing act cannot last forever. Eventually, the star runs out of fuel for fusion. When this happens, gravity wins the battle. The core collapses in on itself, triggering a shock wave that rips the star apart. This explosion is what we observe as a supernova. Not all supernovae are created equal. Astronomers have classified them into different types based on their light curves and the elements detected in their spectra. The two main types are Type 1 and Type 2. Type 1 supernovae are thought to occur in binary star systems. A binary system consists of two stars orbiting each other. If one of these stars is a white dwarf, a dense remnant of a sun-like star, it can steal material from its companion. This stolen material piles up on the white dwarf's surface. If enough material accumulates, it can reach a critical mass called the Chandrasekhar limit. This triggers runaway nuclear reactions, leading to a catastrophic explosion that obliterates the white dwarf. Type 2 supernovae, on the other hand, occur at the end of a massive star's life. These stars are at least 8 times more massive than our sun. As they run out of fuel, their cores collapse under their own gravity, leading to the supernova explosion we discussed earlier. Section 4. Unlocking the secrets theories behind the explosions. The exact mechanisms that drive supernova explosions are still being investigated. However, scientists have developed sophisticated models and theories that explain many aspects of these events. For Type Ia supernovae, the Chandrasekhar limit is crucial. This limit, named after the astrophysicist Subramanian Chandrasekhar, represents the maximum mass a white dwarf can have before it becomes unstable. Above this limit, the electron degeneracy pressure that supports the white dwarf against gravity can no longer hold. For Type 2 supernovae, the core collapse model is the leading explanation. As the core collapses, it bounces back, creating a shockwave that travels outward. This shockwave is initially stalled by the infalling outer layers of the star. However, neutrinos, ghostly particles produced in the core, are thought to re-energize the shockwave, leading to the star's explosion. Section 5. Supernovae's grand role shaping the universe. Supernovae are more than just celestial fireworks. They play a crucial role in the evolution of the universe. They are the primary source of heavy elements that are essential for life. Without supernovae, the universe would be a very different place. During the explosion, intense temperatures and pressures allow for the creation of elements heavier than iron. These elements are then dispersed into space, enriching the interstellar medium with the building blocks of planets, stars, and even life itself. Moreover, supernovae inject vast amounts of energy into their surroundings. This energy can trigger the formation of new stars and influence the evolution of galaxies. The shock waves from supernovae can compress gas and dust clouds, leading to gravitational collapse and the birth of new generations of stars. In a sense, supernovae are both destroyers and creators, shaping the universe we live in.